Page 149. If you look at the bottom right hand corner, here's what the textbook says. The standard error of the mean is the standard deviation of means from many different samples. No, not really. I can calculate the standard error of the mean from one sample. There it is. So that statement is misleading. And now, but put in the right context, it makes some sense. And so let me try to describe that context. Let me describe this example. You've got to bear with me on this. Suppose that we went out in a parking lot, and excuse me, I want to check my time. Make sure I want to make sure I had some disk space left. Okay. Suppose we went out in the parking lot and looked at the first numerical digit that appeared on each license plate. All right, and so there are 10 numbers, 0 through 9. Write those down and come up with a sample from the parking lot of single digits. Okay. Now the average of 0 to 9 is 4.5. So suppose that we went out one day and the first mean was 4.52. Suppose we go out another day, take another sample. We look at the first digit that occurs in each license plate, write it down, calculate the mean, the average. Suppose the second day comes out to be an average of 4.29. Maybe the third day is 4.91. I'm just making up numbers here. 4.56, 4.47. All right, so if we repeated this day after day, went out and took these samples, day after day after day, you'll find the averages are around 4.5. Now, if you were to plot those out on a histogram, you would find that the means from many different samples, the means of these many different samples would tend to be normally distributed. Here's 4.5. But each day you won't see necessarily 4.5, you'll see something that's a little bit off. Now, this in itself is incredibly important to statistics. This idea that the means of samples tend to be normally distributed is called the central limit theorem. And so it says that it doesn't matter what the distribution of numbers in a sample are. And those license plate numbers are all pretty well evenly distributed. We would call that a uniform distribution. But when you take the sample means of any types of data, you find that the sample means are normally distributed in a bell curve. That's so important because it means that we don't need a lot of theorems and charts to do statistics. We can work off a couple of them. And the normal distribution is a big one. So I'll probably talk about that again in Chapter 5, the central limit theorem. Anyway, these means of samples, if I collected a bunch of these means of many samples, will have their own standard deviation. And their standard deviation is going to be the standard deviation that you find in samples divided by the square root of the sample size of those standard deviations. So if we went out and looked at 100 cars each day, took 100 pieces of data each day, well, the standard deviation of those digits divided by the square root of 100 will tell you what the standard error of the mean is for samples of size 100. So anyway, let me give you another example of this that hopefully will make a little more sense. Suppose we wanted to see if Math 160 students were above average in IQ. Okay, now the average IQ is 100, remember, and so the mean IQ is, and I'm going to struggle with letters here. In this case, I'm going to call the population mean IQ is 100. Mean IQ for population. And the standard deviation, I'm going to use sigma as 15. Sigma and S are replaceable here. You can replace this with sigma. Sigma and you're fine. Of course, this is the population standard deviation. All right, suppose that we have a class of 20 Math 160 students. 20 students, and we measured their IQ and got an average of 112. So a sample of size n equal 20 has a mean IQ of 112. All right, now if you consider a single individual person, how unusual is it to find a person with an IQ of 112 or higher? Well, a z-score for 112, the z-score would be 112 minus 100 divided by 15. It would be 0.8. So let's look that up in the back of the book, page 4, was it 449, 459, 659, something like that. Page 649. The area associated, or the probability, tail probability associated with 0.8 of a z-score is right here. It's 0.2119. All right, so the 0.2119. So 21.19% of population has an IQ of 112 or higher. Okay, remember that represented a tail probability. And so here's an IQ of 100, here's 112. So 21% have an IQ of 112 or higher. That's a tail probability. It's not very unusual, is it? You know, 1 person out of 5 has an IQ of 112 or higher. But what is the probability of getting 20 people with an average IQ of 112? Okay, that's the real question. Because in here, in this course, we're not interested in individual statistics. We're interested in a group sample statistics. You're not interested in individual measurements. We want a sample mean measurement. We want to compare it. That's what we want to study, our samples. We study samples, not individuals. So, for 20 people, the standard error of the mean, let me write it here,